All right, everyone. Today we are going to talk about our senior design project. We worked in collaboration with GE Vernova. Our goal was to build an AI-enabled industrial control system. Um, um, this is a quick overview of the project where we had to use a Marxist controller provided us by the GE to monitor to optimize an air monitoring system. We are required to build a test bench, put together an closed box environment, wire up the sensors and connect all the sensors to the GE controller and also send the sensor data to RPI. That it will in turn send the data to AI for further recommendation and will respond back as a recommendation. We were tasked with just writing a prompt which was a rule-based prompt so that the recommendation uh, is under certain guardrails and is not out of any complex system builds. Here we have the block diagram of the system. Just a quick overview is that Mark 6 and RPI are at the center of the entire process, where Mark 6 controls the actuators, which are the fans, um, and the CO2 and the nitrogen sensors to simulate various edge cases or to simulate the environment so that it can be controlled later on by AI. We had a HMI control panel that will control all the fans, and we also had a control board where the user can inject CO2 or nitrogen to either increase carbon dioxide or to reduce oxygen in the environment. So the data from the sensors went into RPI, and then RPI communicated back and forth with LLM, made sure the response was correct, and then displayed it on a GUI. Based on the GUI, the operator will control the control panel and change the actuators, and then the change of the actuators will reflected the improvement in the environment, which will be seen on the HMI. Also, a quick overview of the flowchart of the same process where we start out by reading data from sensors. We check if there was a fault in the sensor or not. If there is no fault, well, then we display the temperatures on HMI. And then also, if has no fault, we'll send the data to LLM to give us a prompt. Now, we verify that prompt for any kind of error. If there is an error, we move on to displaying the LLM output on the GUI, and then the operator makes the changes on the environment. Now, in the case if there is any kind of sensor fault, it will skip the LLM prompt and print a warning in GUI. Or if the sensor fault is not there, but there is a fault in the feedback from AI, then the software loop is broken, and then the G warning is issued on the GUI that there is some issue with the AI and the system needs to be stopped. Thank you.
So this is our final physical build. Starting from the left, you can see our power supply, and hidden behind it is a circuit breaker. From left to right, you have our discrete input and discrete output packs, along with some networking devices, and then the lovely Mark 6E industrial controller. Further to the right, we can see our control panel, which will be touched upon in a further slide. Everything is housed neatly on a panel. Wires are kept in these cable trays and fed into terminal blocks around the back to keep everything nice and neat. One of the main goals of this project was to simulate an industrial panel as closely as possible, so we stuck to industrial color coding for the wiring, as well as neat cabling, in a concerted effort to keep this nice and tidy. As you can see here on the right, all the cables feed out towards this wire harness, which leads to our glass enclosure, which we will touch upon on a further slide.
And this is the control panel on the control board. As you can see, we have all the buttons and lights labeled. Obviously, this is the e-stop. It is not implemented through hardware. It is instead implemented with the Mark 6E controller. The three LEDs indicate the status of the system. Green is system on. Yellow is a warning saying it's out of the set point. and red is system off. This will turn on when the e-stop is pressed or the stop button is pressed. The start and stop buttons turn on and off the sensors respectively. The reset button resets the system after the e-stop is pushed. And then the nitrogen and carbon dioxide buttons release the gases into the chamber with the solenoid.
Continuing our physical build, this is our tank. And so what we can see here is a glass fish tank fitted with a custom acrylic top molded to hold our fans and our input valves. So you can see here that we have a U-shaped acrylic divider in the middle, and that's to distinguish between the input and the exhaust sides of the tank. So on the left side here, these fans are the input fans, and these are the output fans, all wired to the wire harness back on the panel. You may also notice two input valves. These are used to control the input of our gases. So our nitrogen and our carbon gases get inputted through here. Our sensors are held at the bottom, where we feed our data to the entire system, and then we have two fans sitting here to help direct the flow underneath of the divider. So our gases are input here and fed regular oxygen along with the gases inside, and then they are fed under the divider and read by the sensor here, and then they're fed out by these exhaust fans.
And once again, this is the control board. As was mentioned before, all the wiring is done to standard industrial code. A solid blue wire is a 24 volt positive. The white with blue stripe wire is the 24 0 volt. Gray is signal. Red is 120 in. Green with yellow stripe is ground. I had to 3D print and design a mounting bracket to mount this network switch to the DIN rail. Same with the Raspberry Pi. Everything on this board except for the solenoids, which aren't on the board technically, are powered from this power supply, which you connect to the wall. We have blue terminal blocks for 24 volt positive, white terminal blocks for 24 volt 0 volt, and gray for signal. These gray terminal blocks are for the sensors in the chamber. These gray terminal blocks are for the power for the solenoids, which go to the discrete out board and are controlled by the Mark 6E controller in the HMI. Everything is run through these cable trays. Power comes in on the left, and the wire harness comes out on the right.
So here's our HMI screen. As you can see here, we are displaying temperature levels, CO2 levels in ppm, oxygen level in percentage, and then humidity as well in percentage. We're displaying all four of these because these are all of the readings that our sensors take. One is a 3-in-1 where it takes temperature, CO2, and humidity, and the other is oxygen. For the scope of the project, we're really only focused on CO2 and oxygen because that's what we are varying in the system. So that's why we have these colored and bolded. So as you can see here, this is the system in, good, safe conditions. The current CO2 levels and oxygen level is within the safe set point, so you don't see any alarming. And then as you can see down below, we have fan enable and disable buttons. The inner fan, that just enables the two fans on the inside of the container. And then our two input fan enables. This just, all of our input fans and inner fans and output fans are all in pairs of two fans. So we have a total of 10 fans. Each control here controls two fans. So if you trigger the inner fan, it turns on both inner fans. Same thing with the input fans. There's two pairs of input fans. So if you turn on one of these, it'll turn on two fans. Turn on both of them, it'll turn on all four. Same thing with the outputs. So here are our digital inputs. As you can see, we're using this gas solenoid gas for CO2 and nitrogen. These are just buttons on our control panel that we're using to trigger the CO2 and nitrogen release with our gas solenoid valves. And then here we also have a manual reset. That's another button. All of these are actually buttons that are on our control panel. And that's the only digital inputs we're using. So we still have a stop and start signal. That is to stop and start our measurement script on the RPi. Then we also have this e-stop button as well, and that just shuts off everything, disables everything in the system. So for digital outputs, we have things like trip system, out of set point. This triggers the lights on the control panel. Trip systems for the red light that shows the system is currently fully tripped, it's fully off. The out of set point is the orange light. This shows that either the oxygen or the CO2 is out of the safe region, and it shows off, orange light so the operator can tell. We also have the outer fan signals, the input fan signals, and the inner fans. These are the actual points on the relays that is sending the voltage to the fans to trigger them. And then we also have the gas solenoid for the CO2 in the end. That's where the output is actually coming from as well for the DC valve, which we have an external power supply supplying the voltage, but the relay is being controlled by the Mark 6E. And then here we have the Modbus holding register variables. So as you can see, the first four variables, these are the values that are being sent from the RPi. And the first two, or the three percentages, you can tell, these are large numbers. That's because we're actually scaling the values before we send them over. That way, the logic is much simpler. We don't have to use real or float values, which complicates the holding registers. So instead, we just send larger integers, and then we do the logic later where we divide it by 100 to bring it back to its normal value. So like this oxygen here would be 20.88%, humidity 41.07%, and then the temperature is 69.82 degrees. So below that, we have our input fans, these signals, the output fan signals, and the inner fan signals. Now this is just state signals. Now we're using this to essentially tell the AI if this fan is currently on or not. 0 represents the fan is off, 1 represents the fan being on. In our prompt, we are sending these variables to the AI so that it knows the current state. That way it won't tell us to turn on a fan that's already on. And then we also have this read sensors. This is just a signal that's driving the logic for disabling and enabling the sensor reading scripts. And then here we have just an example of what the AI recommendation screen looks like. You'll get a better image of this, of what it's actually recommending in the demo video. So here's a video of one demo of the system. So you can see the system it's on and it's in the correct state. And here you can hear the carbon dioxide being released into the system after the button's pressed. Our sensor reads every 5 seconds. So every 5 seconds, the HMI will update the CO2. As you can see, it's rising up. It's a dramatic increase too because of the size of the system as well as the time it takes to read. And here's the AI giving a recommendation to turn on everything as soon as it goes out of the set point because it sees how dramatic of an increase this is. And then once all of the changes are met, it will say no changes are necessary. Then here we have the out of set point light being enabled because CO2 is out of the set point range. Something that would, in a real scenario, a real industrial setting, would be, a faster CO2 sensor. 5 seconds is pretty fast, but some get a lot closer to real time. They're much more expensive though. So for the scale of this project, we just did, a cheaper, affordable, easy to implement sensor. But in a real time or a real world scenario, you would use a faster sensor, and that would increase the capabilities of the AI as well. And once you see it reaches out of the set point back to safe levels, it starts suggesting some fans to be disabled. We also have that set light returning back to normal. And then it sees the current state, wants you to turn off the inner fan as well. And the prompt tells the AI that it wants the ambient air to return as much as possible in order to save power. So once it is in the safe zone and it's not trending back upwards, it will recommend all fans to turn off to save power.